এখন এসছে সর্বনাশ, তাহলে তো আরো কতদিন এরকম চলবে। অবশ্য আমি কালকে খাবো, আছে কালকে আমি ক্লাস নেব, আমি আবার সোমবার দিন নেবো, ঠিক আছে? তুমি বলে রাখলাম, তুমি খেয়াল রেখো। Okay, so just a small announcement. Tomorrow there will be no class. I will again take the class on Monday. Okay. So as I mentioned in the previous class that today what I shall do is I shall just calculate one more diagram for you, and that diagram is this one. After today, we will go to QE. So this is the diagram which I want to calculate, and so we just apply three vertices. That gives a factor of minus I is equal to Q, and then there will be integrations over space-time integration over these vertices. Here that gives d4x1, d4h2, d4h3. Then we have to call this x1, x2, x3. First of all, I have a minus because of the Fermion loop. We have a loop there that gives a minus sign. That comes both in the Feynman rules in position space as well as in momentum space. We have a minus, extra minus sign with the Fermion loop. Then let me just write this form. This is easy to write. I delta f x2 minus x3 or x3 minus x2. Right? Any way, metric this thing. So this is the propagator for the real scalar field that arises here. And then we have to worry about the Fermion lines. That what I'm doing is I'm writing down the internal part first and also the vertex part. So this will be then ISF beta alpha. Beta alpha. It's not necessary. You can do it. You'll realize why I'm doing the. It gives you more clarity. You can understand the matrix nature of the thing. So you have this, then this is alpha beta. It's 2, it's 1, it's 1, it's 2. That is what you have. And then you have to worry about the external lines. So this line gives you a factor of nk. These external lines gives you a factor of np and np prime. And then you know there will be spinors here. Therefore, for electron we will have 2s bar. Let's just this gamma. The positron is prime. This is the full expression for this diagram, and we just apply. We have written this expression by applying the Feynman rules in position space. So another thing that I missed here, we have this NKP, these factors along with these plane wave factors. One, but this is I. So this these angle factors will also be there. So you're writing the expression of this Feynman diagram in position space. Now, what we shall do, as we have already done in the previous class, we shall now write the Fourier transform of this. We just put this minus sign outside. There is a minus here outside the integer. Then we have the x1 3. Okay. Before writing down the Fourier expansion, I'll do one more thing. You can see that this term basically this it's 2 minus 6. It's closes that place. Now what we are doing is just Fourier transforming this. Fourier transform to 2 4 I. Then I'm writing the same mistake in the Q1 log x2 x3. The Fourier transform of this thing. Then integral go to 5 by 4. Now this x beta this same full factor. Then these normalization factors, then just put it over here. The normalization factors in K and P prime. You can also put 2 bar this gamma P here, and then full integral. After that, let me write down these factors. Power minus I A dot x1 or I dot x times minus I 3. Everything once you finish this full thing, writing this full thing up, you can write these factors. It's fine. So once you write this expression, what we have done is we have done the Fourier transform, and now thing is quite simple. You have to just perform the integrations for these. So this factor, then you have this prime. So what I am doing is I am not allowed to write down the other factors which are not important in the integration. So let me just write down the integration part. So here you can visible? The online people, can you see the board?
Yes, sir. Yes, sir.
So then spatial equations. So spatial integrations. So we have to just find what are the equations here. So as minus I a what are these factors? Minus a minus q plus q. Done. So 4x2 minus I q1 x2. And there are the other x2s. So we have minus q3, right? Q3. Other one, another x2. So plus q2, right? Plus q this one. So that is taken care of. We have the integration b4 x3 minus x3 minus q1 so let me just do this plus minus. Very good. That is all. Now you will get 2 pi whole 4 from each of these three equations and the direct whole dimension and direct the function. So what we should do is we should keep a factor of 4 here as we did in the earlier case and keep a factor of 2 pi over 4 also here. Then we have direct delta functions. So let me write out delta 4 1 p c prime. So this one is done. This one is delta 4 a 3 and then this the other integral delta 4 1. I don't know whether I correctly or not. Check with my calculations. I have three Dirac delta functions. So one is q2 minus q3 plus q1. What did I get? Huh? ठीक है q2 plus q1 minus q3. So that is correct. That I got p plus p prime plus q1. P plus p prime plus q1. Okay. q2 minus q3 is k. Anyway, one of the signs I did not get it correctly. Let me. What about this h3? Did I write this correctly?
Yes, sir. Here the IP dot
It will be q1 It's 3 then plus minus. I think this is correct. No? Oh, no. No, minus. This one is plus. This one is plus. That's why. This thing I wrote it. This. Okay, let me go show the full board. I made a small error. See, can you see the full board? When I wrote down these plain wave factors, e to the power minus I p dot x1 will be for this one, and for these two, for the outgoing particles, plus I p dot x3 plus I p prime dot x3. I wrote a minus, so that is a mistake. So this gives you a plus. Therefore, you have a plus over. You have a.
Sir, can you repeat that last part, what you said just now?
Yeah, just look at this part of the board.
Okay, sir.
Let me zoom it. So now you can see it more clearly. This is minus. This one will be plus for this one. For this is plus. And I wrote this one to be minus, but this will be a plus.
Okay.
As it will be
In
plus.
going with a minus p. Okay, yeah.
And that will ultimately lead what you will get finally due to that plus is that in this Dirac delta function here, earlier I wrote this to be a minus, but this will be actually a plus. Then everything is fine. Okay. And now let us first of all do the Q2 integration. Let us do Q2. So what will be Q2? From this, if you do the Q2 integration, then Q2 will be equal to Q3 minus Q1. So then you can get rid of that Dirac delta function. Q2 is Q3 minus Q1. So get rid of this and get rid of the Q2 integral and replace Q2 by Q3 minus Q1. Here also you have to replace Q2 by Q3 minus Q1. So what you will get is plus Q2 is Q3 minus Q1, so you will get a minus Q3 and plus Q1. So this is basically Q3 and Q3 will get cancelled from here. And in this one there is no Q, so you don't need to worry about this. So this one ultimately becomes delta 4 K plus Q1. So you can write it. Now let us do the Q1 integration. Let us do Q1. So if you do the Q1 integration, this one is also 1. Q1 is minus K. So replace this Q1 by minus K. This will also become plus K. And over here, this will become minus K. So everything is gone. Only one Dirac delta function is left. And you can see that you cannot perform this Dirac delta function integration because there is no K, P, and P. All these are external moments. This is a loop moment that. And now one more change you can do. You can since Q3 is dummy, therefore replace Q3 by Q. So this becomes Q. This becomes Q. And you have this Dirac delta function that you can write it over here. Delta 4 K minus P. So everything is done. Okay. So what we have ultimately is the following: we have minus IG cubed. These factors in A, P, prime. Huh? Yes, I write it down. Before that, it's better to write 4K minus P minus P prime. It is better to write this part over here. This thing over here. So this takes into account the vertex part. Vertex you have this. For each vertex you have a factor of minus Ig. So that gives you minus Ig whole cube. Then you have this overall 4 momentum conservation, energy momentum conservation relation that you have to appear along with the factor of 2 pi whole 4 and this. Then you have these external lines, the normalization factors into prime, and then we have this u bar s e. Then you have this thing before q by 2 pi whole 4, which is basically the loop integral that you have. You must have a, if you have a loop, then you must have a loop integral. The factor is d4 q by 2 pi whole 4. You write it this way. Then I delta s k you can replace by plus k or minus k, plus k are same, so this is I delta k. Then we have I is if plus k q and come out. That's it. It's a full expression that you have. Okay, and you can see that this is the mathematical expression for this particular diagram. For this diagram, and this is the expression for this diagram in the momentum space. And you can see that you could have directly written down the Feynman rules in if you, since we know the Feynman rules in momentum space, we can directly write down the expression by using. And now the next task is obviously to calculate this loop integral. So we have to calculate here precisely the loop integration, which we are for the time being we are not doing. So this is what I wanted to do with you, and you can have some more practice if you want. You can try to figure out what this is and try to write down mathematical expression on this one. So you can apply what you can do, you can write it position space, Fourier transform and get to that expression, or you can directly write down the Feynman rules in momentum space and try to see what expression, what is the mathematical expression corresponding to this diagram. Then there is one more diagram corresponding to which is similar to this, it just inverts the fermion line arrows. That is another diagram. So this completes the 4 diagrams, and I think we have calculated this one in the previous class. We have calculated this one in the previous class. We have calculated this today. You can calculate this one and the other one. So that gives you 4 diagrams. There is one disconnected diagram which you can just leave, which is not important. I think that these are the only diagrams that you have. There are no more. That completes the full set. So what I would suggest to you is that you please try to finish up writing down the mathematical expression for this diagram. Please do this one and the other when you reverse the arrows. Try to finish this these diagrams up, write down mathematical expressions by using the Feynman rules, and this would give you substantial amount of practice. What is left to do here, what is important here, what you can calculate at least at the tree level. At the tree level, you have only the vertex, right? And we have already calculated the matrix element for that. And from there, you can proceed and see what you can do at home is you can see how you can extract the lifetime from that matrix element. How you can calculate the lifetime of the decay process from that matrix element. So you can do that on your own. That is not a very difficult thing to do. Once you know the matrix element, the rest of it is quite straightforward. You can do it. And then you can actually calculate all this Feynman diagram technology gives you a way to calculate corrections to that line. You can do that also. So let us finish at this point for today. And from Monday, what we shall do, we shall try to look at quantum electrodynamics. And with that, we shall end the course. And quantum electrodynamics, we shall only look at scattering processes there, because here we are not, this is a decay process. We have not looked at scattering processes. So we look at scattering process in quantum electrodynamics and just restrict ourselves to tree level, not to loops. The tree level calculations are quite simple. You can do it quite easily. So we shall go to the tree level processes. But obviously, you can ask that what would happen if you go to one loop level or two loop level. That is a different story altogether. See, there are quite a book you can look into any book here on quantum field theory, right? You can look at diagrams, but see, just follow this and then try to look at a book. That will be helpful. But this is what I've done it everything. So I don't think you need to. But obviously, for see, if you do this, this completes the. Now you have to, for any other interaction, for QED I will do at the tree level I will do. But tree level is, you can say, it is quite trivial. So we will do Feynman diagrams there. I will tell you one more subtle thing, an important thing which you should know from the historical perspective also. That is quite important. But for practice with diagrams, you can take what you do is the best way to learn Feynman diagrams is just look up any interaction yourself. For example, in class we have done 5-4 theory, and you cover. Take 5-cube theory and try to draw the diagrams at one loop level. What are the possible diagrams that you can have at one loop or two loops? So you can just try and see, and then look at scattering processes.
How to study the interaction? I mean, let's say for Before, we know the Before potential, we need to do it and we are playing over. So, how can we say these things? I mean, how can we get these interactions? Those are similar.
Okay, you need to say that what is the connection of this interaction? Why is this really you problem? Can you show whether you can calculate the potential? You can do that, but for that you have to look at scattering. In fact, from the propagator itself, you can calculate. You'll be able to do it. It is very simple. It is not difficult at all. You'll be able to show that you get that e to the power of minus mr by r. So you will get that form. That you can do. So, in fact, basically, when you calculate the potential, you calculate it up to first Born approximation. You just put in, you calculate the potential, and you use the first Born approximation, and you precisely get the U power factor. So that is, in fact, means your question basically says why is this interaction phi psi bar psi phi is U power? It shows that the potential is of U power form. From this. So Q is 1 by r. See, it is quite, physically it is quite easy to understand, because you see that your interaction in this case is psi bar psi phi, right? This phi, what it does, you have to understand. So, as I mentioned, that if you look at scattering of two electrons or electron positrons, it will be something like this. So this is the S channel, okay, and this is the mediator. It's interacting, exchanging some particle. That particle here, I am assuming this particle scalar field to be a massive particle. So massive particle means it, you can understand that the potential must be damped by that mass factor. In QED, what is happening is the potential, you have something like this: I bar gamma mu I K mu. So here also you have this electron, say electron positron scattering electrons. Ready? But here the particle that is being exchanged is the massless photon. Massless photon means it is only 1 by r potential, long range, massless. It is talking at long distances, talking to each other. Whenever you have a massive, the exchange is taking place through a massive particle, then it becomes a short range kind of thing. 1 by r times the damping factor. That is precisely the U power. So here the exchange is due to a massive thing. If you take this to be a massless one, then again it will not be U power. So for this to be really U power, this real scalar field must be a massive real scalar field, just to have some mass. If it is a massless real scalar field, so it's like a photon, so to say. Not really a photon, it's a toy photon. Then this will again not be in U power, this will be 1 by r. Because n is 0. So e to the power of factor is 1. It is again 1 by r. So this interaction and this interaction is very similar. Here you have a gauge field. The exchange is taking place. This theory has a gauge impedance. This theory, this phi does not have any gauge impedance. It's a real scale. So that is why you, and it has, if it is massive, then you will have a U power. Okay. Is there a general? No, you can actually show that this interaction is same as U power. This is a U power interaction. The potential is like U power if phi is massive. Okay, so let us finish here. Monday, Wednesday, Thursday, tomorrow there will be no class. We will again meet on Monday.
Okay.